Okay, hello again to this third lecture on DAEs. Today we really start with some DAEs and already some analysis, how we can prove solvability to that. Last lecture we had just basic notions. What is a solution? Then I talked about consistency and constraints. And today we start with linear DAEs, and we will see for that there is some nice theory, and we can apply linear algebra and so on and so on. Anyways, but let's start with that. Instead of this very general DAE that we had before, that we just introduced like this one, x dot of t is equal to 0. So in this very general form, we will now consider very particular forms. So we will consider DAEs of the form E x dot of t is a x of t plus f of t. You may think of how to put this in this very general form, but now that we know that it's just a linear, and then we can express this by means of these matrices. And in fact we have that EA are matrices in, well, I write R. Actually theory also works if we have complex matrices, but since all examples and so on will be real only, I will just use real matrices that has m lines, so m rows, meaning we have m equations, and n columns, meaning this x, as we had defined, the solution will be an n-dimensional vector for every t. So E and A are just constant matrices, and F will be at least a continuous function. We will see that continuous might not be enough to define solutions, but again takes t out of this time interval and returns a vector, so that we can equate these things in R to the m. With possibly an initial condition. Again, we will distinguish between what is just the DAE, this is 3.1, and what is in the initial value problem that is made up of both the DAE and the initial value. But this is just in the general case, x of t0 should be the x0. Maybe as a reminder, we had this time interval to be the interval from t0 to an endpoint. Okay. Well, this is going to be the subject of the next couple of lectures. These linear DAEs with constant coefficients. Constant coefficients means that E and A are just matrices. They don't depend on time. Later we will look what happens if E and A depend on time, but for now they are just constant matrices. Linear, we can write this in this matrix form. Okay, and question will be when there will be a solution to this problem. So what x0 do we need for a solution to the initial value problem, and what f will we need to talk about solutions to this problem. And we will see f will then depend on how E and A look like. And in order to talk about existence of solutions to that problem, we first start with some very basic observations. Observe that for P in R to the M, so matrix P that is invertible. It has that X solves, X is a solution to 3.1, so to these Ex dot is Ax plus F. If and only if, so if it's solution, then of course one can just multiply with P from that side. So this if and only if X solves, well, the same thing, just multiplied by a P. Px dot of T is PA X of T plus P F of T. Well, certainly if X solves this, then this is fulfilled, then one can just multiply with the matrix P, then X will solve this DAE. And the other way around, if if X solves this equation and P is invertible, then from that one can recover the E by applying P to the minus 1, and then we will have that the X also solves this the equation that we started with. Okay, and this is a scaling of the equation, the so-called scaling. Well, just the equations are changed, but what one can also change the X, and this is then called a state transformation. So similarly, let Q in R to the N invertible, then X solves 3.1 as above, if and only if X tilde that we define to be Q to the minus 1 X solves EQ X tilde of dot of T is the same as AQ X tilde without the dot X of T plus F of T. Okay, and this is called a state transformation because here the state is changed. But if Q is invertible, then it's easy to see that no matter whether we have a solution to this problem with the EQ matrix and AQ matrix, then this solution uniquely defines a solution to the 3-1 problem, and the other way around. If X solves this problem, then we can define this X tilde by, so to say, applying Q to the minus 1 to the X, and then we put this in here, and then it's easy to see that this is exactly and this is very helpful for solution analysis. Because for many reasons, we will see a few of them. Then, but we will make this so this is helpful for solution analysis, and next we formulate a mathematical way to characterize these scalings and transformations. So we will make this operational. So we will provide a mathematical framework for these scalings and transformations by means of equivalences of matrix pairs. And here the important thing will all be in this definition 3.1. Here we say two pairs of matrices E1, A1, E2, A2 of the right dimension are called strongly equivalent. The important part is now the strongly equivalent if there exists P in R. Okay. Anyway, so P in R to the MM and Q and R to the NN invertible. So that E2 is P E1 Q and A2 is P A1 Q. Okay, and you see this is those two operations that we make here. So either scale E and A by the P, then this will mean a scaling of the equations, or we transform the state, and this amounts to well, a right multiplication by Q of E and A. Okay, and for that there is a lemma. Why this is now a nice thing, the relation so then we write EA1 is strongly equivalent to E2 A2, and lemma then says that this relation defines an equivalence transformation. Yeah. And well, this will be an exercise. Basically, what is an equivalence transformation and why this is particularly an equivalent transformations. And now why this is interesting for us. Well, we will work towards canonical forms, and a few remarks on that. Well, it says that E1, A1, E2, A2, if they are equivalent, it means they define the same solutions. As I had it two slides before, that if they just differ from a scaling or for a state transformations of the DAEs that they describe, meaning if E2 A2 is equivalent to E1 A1, then it doesn't matter whether one considers this DAE or that DAE. How do we write this in positive forms? Doesn't matter. Oh no, that might be misleading later. So they if they are equivalent, then they define the same solutions of the DAEs, and then for analysis find, say, e tilde span e hat a hat that is equivalent to e1 and a1, and also then of course e2 a2 with ea a hat being nice. Okay, nice is not a mathematical term, but we will talk on that. And in this, but for us, this nice means that nice structure, basically a nice structure. And this will be then this canonical form. I think in the script I rather said that once one has such an equivalent relations, then one defines equivalence classes. Equivalence classes means that they contain all those elements that are equivalent to each other, and then like finding this e hat a hat is finding a representative out of this class which represents the class in a nice way. And here in the script I said, well, it has a nice structure, and this means can be used for analysis. Well, and then because it's, if one does then analysis for this e hat a hat, then immediately because of this equivalence, all analysis done for e1 a1 as well, and e2 a2 as well, and all others that are equivalent to here. For our purposes, this will be the canonical form. Yes. Well, thing here is that it's nice that there's no real definition. Maybe better say useful or appropriate, but it's not fixed. So there can be many canonical forms that you may like. But for our purpose, we will use this Kronecker canonical form because it works very nicely to do solvability analysis for this DAE. That is defined through EA, through the E and through the A. This is one very important theorem. So let E A in, now we really need the C because now we talk about eigenvalues, and then we better use the complex matrices because they are complete. They can be diagonalized and over the field of complex values. So let those be very general. Of course, then they can be also real. So let them EA and CMN, and then the theorem says then there exist those non-singular PQ, P again in CMM, Q in CN times N, such that for all lambda and the complex numbers, we have that P times times lambda E minus A times Q. So this matrix from the left and from the right, that this we can write as such a block diagonal matrix with some L blocks, and here we use epsilon 1, L epsilon P. Then there were blocks with the index eta 1, block block eta what? Why don't I see this? No. Okay. Q. Then there were those J blocks with the index row from 1 to J row up to R. And then there were these N blocks, sigma 1 to sigma S. Okay, so I'll tell you in a second what are these L blocks, J and N blocks. But first let's start with why is there now suddenly this lambda E minus A. That's now maybe a short regression that one may nicely distinguish E and A by writing this through the brackets, but is an equivalent writing of that would be lambda E minus A, because this is useful and one can just write this as one matrix, and all terms that are multiplied with the lambda will be those that belong to the E, and those that are not multiplied with lambda will be those terms that that are from the A. So from this writing, this is a compact writing for writing these matrix pairs. This has some other nice properties, with, for example, with eigenvalues and so on. Okay, but well, this basically says that EA is equivalent to matrix that relates from PAQ and PEQ. Okay. Okay, now what are these E and L blocks? Where so the L blocks, L epsilon, call them, they look like lambda. So this, yeah, again, lambda is what belongs to the E. They look like lambda, a 0 and a 1, and go to 1 and go. So they have this they have more columns than they have rows. So they look like that. These are the lambda blocks, and they have more columns than rows, but yeah, we will have examples in the exercise to see what strange forms they can use, because here we have they are in C N times
n plus 1 and n greater or equal than 0. So n can be 0, and then, well, they are not like they have no row, but they have columns. So then they really degenerate in just a line. But we will have examples on that. Then these eta j blocks, they look like the transpose of them. They have more rows than columns. 0, 1 minus 0, 0, 1, 1 again, and they are in C n plus 1 times n. And now the so-called more regular blocks, these J, they are standard Jordan blocks. We have the row J, they look like lambda times identity blocks, and then they have these Jordan blocks, lambda J, 1. I hope you had this in linear algebra, or you had this numerical linear algebra. Then we had this. You can factorize. No, how do you call this? Decompose matrices in Jordan chains and Jordan chains, and this is one of these Jordan chains. But those are now perfectly square matrices. And here the n will be greater or equal than 1. Here it still can be greater than 0. And then there are these Jordan blocks with respect to the eigenvalue 0. Just see there's a typo in the script. I will. 0 there. Minus 1, 1. And they are also perfectly square blocks. So and that's what the theorem says, that for any such EA in the complex matrix, m rows and columns, you will find matrices so that you can find the equivalent matrix pair that has this particular form. It's block diagonal, and the blocks, they have this structure here. And I have to add a few remarks on that. Remarks. The canonical form is unique up to permutations in the order of the blocks. And well, this means that one can of course swap these blocks, and then still one will have the Kronecker canonical form. But other than that's unique. And I won't give a proof. It's very technical. And one more thing, notorious for being difficult to compute. So it's not a good idea to compute these Kronecker canonical forms by means of the with a computer. But very useful, and we will base a lot of our considerations then for the analysis. Okay, so much for this lecture. Have a look in the script. There, the formulas are better displayed. Well, next week there will be an exercise sheet, and then you can compute such a canonical form on the paper and analyze that, and we will go on and see how this canonical form provides quantifies the DAEs and how it provides solutions. All right, thank you.